Good morning, good afternoon, and good evening. Welcome to TESI, my YouTube channel for theoretical and experimental scientific investigations. My name is Gabriele Barbaraci, and today I will guide you through the mathematical modeling of the current induced into a thermoelectric generator tile by an AC magnetic field. The agenda of today is characterized by an introduction in order to describe what the thermoelectric generators are. We're going to switch the fundamentals in order to give an historical background related to the physical law describing the behavior of the thermoelectric generators when they come into contact with the outside sources. Then we had to build a benchmark setup because we discovered something that the magnetic field, the AC, generate current on this kind of systems. So we had to produce a design, manufactured with a 3D printer. We had to show the specs of our components and the wiring connections. After that, we're going to perform some experiments in order to describe the different dynamic behavior when the thermoelectric generators are faced towards the AC magnetic field source. And at the end, but nevertheless, is the most tough part for some of this try to explain mathematically the behavior of physical systems, the math modeling. We're gonna make modeling of the magnetic field, of the voltage analysis, the eddy current, which is the toughest part of this video, and that's the reason why we broke this session in two parts, part one and part two. And finally, the parameter identification, which allows us to avoid strong nonlinearities coming from the orientation of the TEG tile as related to the direction of the magnetic field. Before to start the discussion, I would like to forward my special thanks to Lab Center, which provides the sponsorship for my YouTube channel with a license of Proteus, one of the most advanced and professional printed circuit board design software that allows us to perform different experiments and is still wide used between the great scientific community and industries such as Lockheed Martin and renowned universities. All right, so what are tactile or rather thermoelectric generators? Those are simple physical systems that convert heat in current and or, for better say, current in heating or rather thermal gradient. In other words, if I give a hot temperature here and cold on the bottom, I generate current running through this wire. I can make this system to work in an opposite direction. I can get current and then generate a thermal gradient through the entire thickness of the system. In this picture, we see TEC. Basically, there is a code 12706, which means 127 a couple of PN joints, positive and negative doped material, 127 couple. We will see later what is that. And the maximum current that this system can work is 6 amp. All right, the historical background is very simple. They see this material in two different aspects. We have said before something that is related to these two scientists, Peltier and Seebeck. If we give current to the systems through the Peltier coefficients, which are related to the particular material that characterize the PN junctions inside the tactile, right? Give a certain thermal flow through the entire thickness of the tile. However, if we give a gradient temperature, sorry, my English sometimes is very bad, temperature gradient through the thickness, right? Through the Seebeck coefficient, we are able to generate electromotive force of the electron. In other words, we are able to generate current, right? Now, I have seen this system in a very curious way. I was just kind of fascinated because, we have electromotive force and we have a current. And I said, but in the previous experiment, we have seen that a variation of magnetic field generate an electrical field distribution in a spatial way, right? And since that we know that the voltage is carried out by the circuitation of the electrical field through the infinitesimal pattern of the electron motion, the questions rises spontaneously. What if I use James Clerk Maxwell to link these two physical laws to create a new one. We have to perform the experiment and we will see what happens. It's time for the experiment. Right, here the experiment. So we have the thermoelectric generator here that by rotating should develop a different voltage. Actually, the status field is turned off. Now let's fire it up. There you go. Now, as you can see, here I rotate and it change, and the voltage change. So when it is horizontal, right, the flow is parallel to the normal of the surface. But when I turn it, like for example 45 degrees, roughly like this, all right, the voltage decrease, increase, decrease again, okay, and it become almost zero, like this, right? Then I rotate clockwise until I reach again the horizontal position. The voltage maximize the value, and then it decreases it by increasing the angle towards the clockwise sense and also counterclockwise. So standard field is powered directly from the transformer in AC configuration. Now we start to mathematical model that problem. In the video, we have seen the fixture red, where it is coupled with the orange fork holding the tactile. Notice that in our case, we use a 127 couple and 9 amp of maximum carriage amp. On the right side, there is a table describing the physical parameters for the stator field, and the forks allows here to rotate the tactile inside the stator field chamber. In this picture, we can see the capacitor plate that are used in order to extract the voltage along the X and the Y direction, because we will see that we're going to need the expression of the magnetic field in order to identify the signal coming from the tactile. The capacitor plate has a specific geometry and is not symmetric because, as you can see, the distance between X and Y direction is different. So we have a 46.51 and 44.61, but careful because they are subjected to very strong tolerances due to the fact that when the print cools down, it tends to deform the shape, the initial shape. So I reported some of the dimension in this table in order for you to describe and carry it out by yourself eventually with some very trivial calculations, the value that we are talking about in this presentation. The benchmark setup is characterized by our oscilloscope that we've seen in the previous video, as well as the power transformer. But the new component is here, the thermoelectric generator, which has been designed by using flatness tolerance in order to have a more uniform thermal flow. There is also a specific geometry of the tactile. It's a 40 by 40 millimeter red and black wire. I'm specifying this one because if you apply the positive voltage coming from the DC power supply to the red wire, you're gonna have the top phase hot and the bottom phase cold. But if you switch the two wire, you put the red on the black and the black on the black and the red, you're gonna switch the side of heat and cold side of the tactile. So here again, we reported the 127 PN junction at 9 amp. Now, after that, we have again imposed the setup for the electrical connection in order to minimize the heat dissipation and to prevent any damage on the coil characterizing the stator field. All right, so from the capacitor plate, we have extracted the signal voltage along the X and the Y direction, and we made sure that these signals are those ones coming from the AC magnetic field, which has to be at 60 Hz as described by the FFT analysis. First things to do is to model the magnetic field. But we know that the component is along the Z direction, and the rotor of E, the kernel of the electrical field, is equal to the minor differentiation B along time. So from where we extract the signal of the electrical field, which is related to the potential through this relation. By having this relation and replacing this one in the last equations, we carried out the expression of the magnetic field. So The magnetic field is basically by the difference of the two amplitude voltage across the capacitor plate, multiplied by cosine of omega t minus phi over the area, over the distance x dy, and by omega, because we have integrated, plus a certain constant. Now, assuming that we have rephased the signal and imposed the constant 0, we have bz over time as a function of time, like a d0, or rather the amplitude times cosine omega t. All right, now we have to carry out the most important things. We had to adapt the signal voltage by having a different angular position of the thermoelectric generator across the direction of the AC magnetic field. We have seen that by rotating the thermoelectric generator or the tactile, we have discovered a different voltage amplitude that can be summarized here in this diagram with a different color. And we made sure also that he's a isofrequential by doing the FFT analysis. Here in this table, we have reported the different voltage amplitude varying the angle 0, 45, 90, 135, 180 at the same frequency, 60 Hz equal to 377 radians per second. Okay, we have seen and said that inside the thermoelectric generator, there are 127 PN junctions. PN means positive and negative doped material respectively. They are connected one to another through a copper plate, which I have reported in a macroscopic configuration in this image, where we have A, B, and C respectively the size, the 3 dimensions of the copper plate. And moreover, I have indicated the presence of the BZ component orthogonal in this plate. And I never used, and I will not use the cosine of the angle, because every time we use the cosine of the angle, we incur in the introduction of nonlinearity. I have conducted the scientific investigations by introducing a parameter that allows us to identify the voltage by avoiding any sine and cosine in the characterization of the electromotive force. As a matter of fact, starting from the Maxwell equation, I have included the eddy current value in terms of current density, as well as the magnetic field, because the flow generated by the magnetic field in this plate at the same time it generates a counter flow that it is shown in terms of vector j which has component along the y and x direction. So the curl of the eddy current and magnetic field generate a certain current density, which characterizes the pattern as described in this image. That at the same time they generate a magnetic field. Now we can substitute to J an expression where the current density is developed by the curl of a certain vector functions, which is a lower phi xy, or rather as a function of a xy plane, times sine of omega t along z direction. Now, since that we know that the rotor of H is equal to J and J is equal to the rotor of that function, I put everything inside the same parentheses, and by eliminating the rotor, I can assume that the rotor of the gradient is zero. So I can introduce a further gradient function x by z multiplied by sine omega t. What we obtain is the magnetic field as described in this expression, where the gradient of gamma is equal to phi xy g sine of phi xy times g along that direction. By knowing the electrical field and the expression that we have found in presence of the Ohm law in terms of current density, we obtain a first order differential equation in terms of current density along the x and y direction that will be also replaced by the knowing that cosine omega t is equal to j sine omega t. So after this substitution, we obtain a second order differential equation non-homogeneous in the variable phi x and y. This is called inhomogeneous Helmholtz differential equation. This is characterized by an homogeneous solution and a particular solution, which will be described in the second part of this video.